In this video, we're going to talk about some of the basic principles behind a laser, but also reemphasize the conditions during which light can interact with matter. So we start off with an atom, a single atom, and that single atom has two possible states, quantum numbers 1 and 2. So 1 is called the ground state, and 2 is an excited state. And for simplicity's sake, we're only going to look at two states for right now. Now what we're seeing is that light's coming in, and occasionally, if it's on target, then it's going to get absorbed. And the condition for that absorption is that the energy quanta carried by the incoming photon matches up with the energy difference between the two quantum numbers, the energy difference between these two. Now, this is interesting. It looks like we have a tool to change that energy level. But unfortunately, because the energy of the incoming quanta doesn't match up with the energy difference between the ground state and the first excited state, then it's never going to get absorbed. Now we could change that a little bit. We could change the color and see if we could match that. Oh, and you can see we got there because we got a little blinking action happening. Right here, it's kind of hard to see, but that shows what the energy level of the photon is. So we went just a little bit high. There we go, we got a match. So now an incoming photon gets absorbed and then gets re-emitted. It sort of underlines a central principle that you've probably heard way back in elementary school, maybe in middle school science, that if something is good at absorbing a color of light, it's also really good at emitting that light. So kind of a little oversimplification, but makes sense in this case. So let's now reset and get back to where we were and talk about the difference between stimulated emission and spontaneous emission. So far, all you've seen is spontaneous emission. What are the keys for that? Well, if we take a look at the photons that get emitted, that we want to take a look at the direction they wind up going. So that was kind of random. And we also want to take a look at the timing that it happens. Now, right now, the time it takes for that emission to happen is pretty random. It's governed by a time constant we call a lifetime. So I'm going to change and make that lifetime shorter, and let's see what happens. Yeah, so the re-emission happens almost instantaneously. If the lifetime is longer, then it's going to stay in that excited state for a little while and then spontaneously re-emit. Now, I'd like to see what would happen if we could increase the number of photons that we have. So you're just going to increase those. Okay, so now we see transitions happening quite a bit. And I'm going to pause this for a second and just take a quick look at what those emissions look like. Look at these photons traveling in pairs, in pairs, in pairs. They're headed in the same direction, and they're also in phase with each other. So let's study this phenomenon one more time. I'm going to back off the lamp controls a little bit and then press play. And you can see that the time that it takes for the emission to happen coincides when a new photon comes in. And when a new photon comes in, while it's in an excited state, it's going to stimulate emission. Not spontaneous, stimulated. So once again, stimulated means that our electron was in an excited state and a photon of exactly the right frequency and energy came nearby while it was in an excited state, and that triggered or stimulated the emission of a photon from n equals 2 down to n equals 1. And then they go off in a pair. So that's how we can tell stimulated emission from spontaneous. Right, so let's take a look. Let's see if we can rule it as stimulated or spontaneous. All right, here comes one. We're missing pretty badly here. Okay, right, and spontaneous because it went in the wrong direction. So let's make a few go a little faster. And stimulated, we can tell because they go off in pairs together in the same direction. Okay, so spontaneous, random direction, and it spontaneously, the electron spontaneously jumps from n equals 2 to n equals 1. Stimulated emission, because it's triggered by an incoming photon, and then we have a pair of protons that go off together. Okay. Good. Now let's go to multiple atoms. Well, we have a flood of lights up here. Let's go ahead and turn that on. Let's see what happens. Let's see what color it is. Well, in this case, the color of the incoming light is a dark blue, which is going to be a high energy photon, and it corresponds to the energy difference between state 1 and state 3 on our energy level diagram. But then we see that it's possible for emission to happen when we go from n equals 3 down to n equals 2, which is a pretty small jump, and that would be infrared. That's what these sort of like pinkish particles going off are. So that's infrared. That corresponds with the energy level difference between 3 and 2. And then from 2 down to 1, those are our red photons. Okay. So here we go. We have all of them all together. And we have blues that are going off because that's a spontaneous emission from 3 down to 1. Then we have some reds heading off in different directions, and that's a transition from 2 to 1. And then we have some that are transitions from 3 to 2, and that's sort of these infrared ones. Okay, now let's talk about spontaneous versus stimulated again. In a laser stands for light amplification through stimulated emission of radiation. So that's the key. We want to focus on that stimulated part. But in order to be ripe, to be stimulated, we need a population that's pretty high in that wavelength that we're looking to trigger. So what we're going to do then is that we can actually see that there's lots of evidence of stimulated emission going on, because anytime you see photons heading off in pairs, that was stimulated. But what if we play around with these lifetimes a little bit? See, what we want to do is really create lots and lots of n equal 2 states so that they can get triggered by other red photons. So if we take this lifetime and turn it way down, then we see we have lots and lots of reds. And when we take a look at our diagram, we have lots of reds heading off in pairs. So if we turn mirrors on, if we enable our mirrors, then the mirrors are going to reflect red photons back towards the other ones. And so there's actually going to be a preferred stimulation of photons moving back and forth horizontally. And you can see our power of the laser is increasing. I better release that power. And now we're lasing. But I'm going to turn up the mirror again. So the mirror is going to reflect red light back horizontally. And so the stimulated emission of radiation is going to favor light that's moving horizontally, either left or right, and primarily red light. So we're starting to laze again. Now, if I took the lifetime of 3 and I put it way up there, then it's not as ripe anymore. So we don't have as many. I'm going to bleed off the power here a little bit so we can cool down. So we have lots of, because the lifetime for n equals 3 is pretty short, then we have lots of decays of n equals 3. But if we reduce the lifetime for n equals 3, then that's going to increase the probability that we're going to have n equals 2 laying around. And because the mirrors go back and forth, then the stimulated emission is going to be favor horizontally moving light. And then my power is almost too high. I better bleed some off. Oops, too late. So that idea about bleeding some off is where pulsed lasers come from. All right, so let's see if we can set that up again. We'll reset all. Right. I'm going to turn this light up. So we're pumping this. We're pumping this with blue light. So we have n equals 3 and n equals 2 states available. We're going to turn down the lifetime of n equals 3. We're going to enable mirrors. And with reflectivity set to 100%, no light ever comes out. So I'm probably going to let a little out, but not until we build up lasing capability. Right. Now it'd be nice if we could get this to happen on its own without blowing out. So I'm going to back off on the power a little bit. And now we're lasing, and our power levels are pretty stable. So that looks good. Now your assignment is going to be to try and get this laser to be in a different color. And you'll want to think about what properties you're going to want to change.